I will tell you about dark energy and our faster universe. So this is a brief summary of my talk. I will start explaining the minimal options for dark energy. Then I will talk about coupled cosmologies and the rest of the universe, their role in cosmological tensions, and finally I will finish with some ideas for collaboration, potential collaborations. So as you know, our universe is expanding at an accelerating pace. There are many pros about that. I mean, we have non-negligible luminosity distances, CMB measurements, large scale structure. Well, if Einstein's gravity holds on ultra-large length scales, then, assuming that this happens, the simplest explanation for current cosmological observations is to assume the existence of a dark energy component with an equation of state smaller than -1/3 in order to ensure cosmic acceleration today. So the simplest or the most economical explanation or description of the nature of this dark energy component is to assume the existence of a cosmological constant representing an invariant vacuum energy along the universe expansion history. So this cosmological constant was introduced by Einstein in order to have a static universe, but when Hubble discovered the expansion of the universe, Einstein refers to it as his biggest blunder, right? Okay, so in the cosmological constant case, the equation of state is -1, is constant, okay? And the problem with the cosmological constant is that it has a huge fine-tuning problem. When one tries to compute from the quantum field theory approach the expected value of the vacuum energy, what happens is that one obtains the naively expected value exceeds the observational one by more than 120 orders of magnitude. This unfortunate situation has been dubbed as the cosmological constant problem. And not only this, a related problem is the fact that why the dark matter and the dark energy densities are so close to each other today, right? This is the so-called why now problem or cosmic coincidence problem. Indeed, if I show you here the cosmic pies from Planck for a lambda CDM universe, right? There is only 1% chance that an observer living in a randomly selected logarithmic expansion interval in the history of the universe would be lucky enough to have dark energy and dark matter of the same order of magnitude, okay? So this is clear a huge problem, right? And we have a huge problem and we need to solve this, okay? So in 10 years ago, I did a poll, and the question I asked is what ingredient accordingly to I asked 100 cosmologists, what ingredient in your opinion should be changed in the lambda CDM model? And at that time, neutrinos were not still introduced as massive particles, they were fixed as massless ones. So 90%, almost 90% thought that the neutrinos, but 25% thought more or less that the dark energy sector should be modified. I guess that today this low percentage of curvature will be much higher, but okay, I mean, so anyways, I will repeat this 10 years later. So there were very, very nice answers, like the question is whether the real world is just lambda CDM, my money right now is on W-1, we need to give neutrino masses, we will need neutrino masses. I'm also prejudiced at the fact that in my lifetime, so I mean, there were very nice questions, I will do this. Anyways, so it's clear that we need to enlarge the dark energy sector. The simplest, well, one possibility, an appealing avenue is to assume that dark energy is something dynamical, okay? So one can assume the existence of a quintessence field, a cosmic field, quintessence, slowly rolling down towards the minimum of its potential. However, quintessence fields are not better these sort of models are not better than the cosmological constant case concerning the fine-tuning, as there is no fundamental symmetry setting or imposing the tiny value of the potential at its minimum, which is set by hand, okay? So in practice, what one does is just to assume an equation of a state which varies in time, right? Here are the best, the mean values together with the errors the Planck collaboration, and you can see that they are perfectly consistent with a value of with a current value for the dark energy equation of the state of -1, and a time derivative 0. I mean, with a cosmological constant. So let's go to the landscape. Cosmic scalar fields, as the quintessence field in nature, if they are present, they should couple to the other fields, right? However, the strength of interactions between ordinary matter and quintessence field are severely constrained by observations. So, however, couplings among the two dark sectors themselves, right, between the dark energy and the dark matter, are still allowed by observations and are a very appealing avenue. Okay. So notice that if we assume that what happens if we parameterize the interactions of dark energy and dark matter in this way, they follow the same evolution in time. They no longer evolve as independently. They are coupled. So they follow a similar evolution in time, and in some sense they address the why now problem. Okay? T mu nu here are the energy momentum tensors, and Q encodes the dark energy, the dark sectors of the coupling. That is the interaction rate between the two dark sectors. Okay? So a potential problem of these cosmologies is that they must suffer from early instabilities due to the presence of Q in the dark energy pressure perturbation. Here I show you, if I define the Doom factor in this way, in the dark energy perturbation equation, this Doom factor, if it's positive, it acts as an anti-damping source, triggering an exponential runaway growth of the perturbations, leading to a non-viable universe, okay, because the universe won't be stable. Okay, so our recipe is to keep this factor negative. Okay, otherwise we will have these large scale instabilities, and these models won't work. There are plenty of models in the market, as in any other possible theory, right? Susi, whatever. So I mean, we have plenty of models, more complicated, less complicated, and also this coefficient sigma can be proportional either to H or to H0. And if it's proportional to 1 plus W, the model will be stable for any choice of the dark energy equation of the state, okay? So, regardless, well, I mean, this theory should be considered as pure phenomenological scenarios, okay? But then there are possible field descriptions at the classical and quantum levels, okay? And indeed, quintessence models can be written as scalar tensor theories, and gravity theories correspond to generalized brand D theories with a brand D parameter either equal to 0 or equal to minus 3 halves if we go to the metric affine formalism. Okay, so we can do a matching in principle between coupled cosmologies and quintessence coupled cosmologies, and also between quintessence coupled cosmologies and modified gravity theories. Okay, in the Einstein frame there is a scalar field, and the energy momentum tensor is proportional to its pole velocity. Now let's see what this implies. Okay, so there are in general two types of models. Okay, for interacting dark energy. We have models in which the momentum exchange is parallel to the dark energy velocity, and there are models in which the momentum exchange is parallel to the dark matter velocity, okay? And then they can be proportional either to raw dark matter or raw dark energy, but I'm talking now about U mu d or U mu dark matter. And a very important thing here is that in dark energy velocity models, right, the acceleration of dark matter particles and baryons are different, okay, due to the equations. Okay? There is a term there, right, in which the momentum must be conserved, right, in the dark matter frame, for instance, always, right. So there is a fractional increase in the dark matter velocity here in the Bell models, in models in which the interaction rate is proportional to the dark energy for velocity. Okay. So this implies that they are like quintessence models, and this implies the existence of a fifth force effect. Okay, there is a fifth force acting in the dark matter sector. Okay, in this sort of models. So apart of the other cosmological constraints that we can put, these models violate the weak equivalence principle, okay? ¿Qué es el uncambio? Gonski studied the observational consequences of such a violation, of the violation of the weak equivalence principle by observing dark matter-dominated galaxies orbiting much larger host galaxies. And what they found, using tidal streams, is that you realize that for the strength of the gravitational potential, which is Yukawa-like, has a term that is beta squared. They found that dark matter and baryons should not have accelerations that differ by more than 10%, implying a limit on this beta parameter. So we can constrain this some sort of models, also using weak equivalence principle violation arguments. Okay. So let's see now if there is any evidence today from current data for such an interaction. So in a recent study, we found that using the most complete and up-to-date CMB datasets, that an interacting cross-section is always favored with 95% confidence level significance. You can see here all that the value of the coupling is always, a negative value of the coupling is always favored right there, okay? So the responsible for this preference and also for the improvement with respect to the minimal lambda CDM model are the poles, okay, the responsible ones, due to the lower amplitude. You can see here in this plot that since they prefer a lower amplitude at high multiples, the interacting cross-section model, the interacting dark energy model is favored over the minimal lambda CDM one. Here I show you also the residuals with respect to the minimal lambda CDM model. So, after considering biodata, as we know, biodata always restore things back to normal. So, I mean, this preference for interacting cosmologies dilutes somehow after considering baryon acoustic oscillation measurements. However, I mean, think about this. I mean, if there is an interaction between dark energy and dark matter, the logical thing is to think that W is not -1, right? Simply because, I mean, if you have there some interacting dark sector, the dark energy equation of state, you are expecting it to be different from -1 just because it's interacting, right? So if we allow for more freedom in the dark energy sector, what happens is that the preference for a non-zero coupling still holds even after considering baryon acoustic oscillation data, okay? If we consider W smaller than -1, a phantom interacting dark energy is also mildly favored, sorry. And the related question is another one. Is there any preference for a particular model? The answer is yes. Among the models that I have shown you before, models 1 and 2 are equally preferred, and very close to lambda CDM. Okay? And as I told you before, the addition of baryon acoustic oscillation data tends to restore the value of the parameters to the default values in the lambda CDM model. The question here is, would it be the same situation if instead considering baryon acoustic oscillation data, that is geometrical information, we consider full shape power spectrum measurements? The answer is, in constraining these cosmologies, full shape measurements are way more effective than baryon acoustic oscillations because they have extra information. In the broadband power spectrum, there is extra information, and you can see clearly here that the constraints are tighter, okay? So I mean, the fact that they are sensitive to the matter density, to the matter radiation equality scale, makes this sort of measurements more powerful, okay? Full shape power spectrum measurements. Let's see what happens with the rest of the universe, okay? So we have Malam curvature, radical dark matter, the neutrinos. What happens if we consider more stuff, right? So let's start with close cosmologies, for instance, right? So current CMB data shows a clear preference, right, for a closed universe. So while the compatibility of a closed universe with Planck data is solid, the fact that we have a curvature makes the Hubble constant problem tension worse, and also implies attention between Planck observations and large-scale structure data. So interacting cosmologies can solve the discrepancies between this Planck data and other data sets in closed cosmologies, rendering these scenarios are very appealing ones because they can solve a number of tensions in different fiducial cosmologies, among them closed cosmologies, okay? So indeed, there is a preference for both a closed universe and a coupling at 99% confidence level. There is a very significant improvement, right? And you can see this clearly here in this figure, in which you can see that there is a degeneracy indeed between the curvature of the universe and the coupling between the dark sectors, okay? So, indeed, if we go to variation analysis, we have the variance factor indicating strong evidence, favoring the interacting dark energy model plus a curvature over the closed universe one. And you can see this here, for instance, in the Planck plus Pantheon data, we have a 3.2 variance factor, okay? So there is strong evidence for this, and interacting dark energy cosmologies are able to solve a number of tensions, okay? So what happens if dark energy, instead of interacting with dark matter, interact with baryons? In this case, we need to modify the Boltzmann equations for baryons in order to account for the dark energy baryon elastic cross-section, okay? Elastic scattering cross-section. The question here is, how large can it be, this cross-section between baryons and dark energy? Okay, so of course, there are independent searches apart from the cosmological ones. For instance, I show you here the two less suppressed 8-dimension effective field theory operators. T mu nu is the standard model particle emitting momentum tensor. Phi is the quintessence field, and 1 and 2 are two suppression scales. So Atlas collaboration finds a limit, right, on this parameter alpha xv, which is the ratio between the cross-section of baryons interacting with dark energy with respect to the Thomson cross-section, okay? So from the non-observation of dark energy production together with the TT bar channel, they set a bound on N1 of 200 GeV, and for the non-observation of dark energy together with jets and missing transverse energy, they set a limit of 1.3 GeV. So overall, it means that this parameter alpha xv should be smaller than 10 to the minus 12 from the non-observation of dark energy colliders, okay? On the other hand, we have also precision gravity tests, such as Gauss experiments, measurements of the Casimir force, precise measurements of the solar system, right? Precise gravity tests in the solar system, and also should be very small. The question is, from cosmological probes, can we also state the same? Notice that, first of all, if W is -1, there is no possible effect in the baryon velocity equation. So there won't be any effect in the case of a cosmological constant. Here I show you the temperature power spectrum together with cosmic baryons and the matter power spectrum for different values of that parameter, the alpha xv parameter, which measures the strength compared to the Thomson cross-section of the baryon dark energy interaction. You can see that the effect is maximal at around a multiple of 5, but it's tiny. I mean, it can be approximated as this parameter divided by 100, but it's tiny, the effect. And the power spectrum is also very tiny, the effect. The effect is based on an effect due in the late integrated sample effect, and also in a drag term that is present in the baryon velocity equation. But the effect is tiny. Also, because W is very close to -1, and because the baryon density is subdominant with respect to the cold dark matter one. So the changes are very small. So even they are very small, even to be observed by future surveys. Okay. So there is no hope to observe a coupling between baryons and dark energy. Okay. What happens with neutrinos? If we add neutrinos to these scenarios, okay, in the interacting dark energy scenarios, we will see this in the talk from Alessandro Melchiorri on Thursday. But what we can learn here is that the bounds on the neutrino masses and the effective number of species are very close to those in the lambda CDM model. In interactive dark energy cosmology, they basically don't differ. I mean, in the case of an effective are the same, and in the case of mu is the mass of the neutrinos is 0.15 instead of 0.12. So neutrino constraints should be regarded as robust, as they don't depend strongly on the fiducial cosmology. Okay, and you can see this. Now let's go to cosmological tensions. Okay, new threads. Now we have here there are new members in our dark energy side. Okay, so we will talk more about this, of course, from Alan this afternoon. But they have a constant tension. I know all of you know there is a disagreement between 4 and 6 sigma, depending on the data set, between early estimates, model-dependent estimates, high redshift from the CMB, and late-time measurements, model-independent from observations of redshifts and distances at low redshifts. Okay, so rather than decrease, it has grown significance with improvement of data. Okay, we can see this in this plot, right? That the error bars have decreased and the tension has increased, right? And there are two sorts of possible solutions, right? One can either go to the early universe and change both the sound horizon and the angular diameter distance to have a higher value of H0, or late universe solutions in which one can only change, obviously, the angular diameter distance at low redshift to have a lower H0. And of course, all these solutions are required to unchange the angular scale of the location of the CMB peaks, the diffusion angular scale, and also the scale corresponding to matter radiation equality, the angular scale. So our cosmologies indeed predict a mismatch between early and late measurements of H0. You can see this clearly here, right? There is a huge degeneracy between the Hubble parameter and the coupling constant between dark energy and dark matter, okay? And one of the simplest scenarios in which the dark sector coupling is proportional to the dark energy, you can see energy density, is able to solve the issue. We can see this here. Regardless if we go to the R16, there, where you can see in that Lister plot, right, or R19, I put you the mean value of H0 with the error bars in each case, okay? So one of the most simple scenarios is able to solve the issue, okay? So indeed, for all the CMB data sets that we have explored, the mean value of H0 is much larger, okay? And the significance of the H0 tension is strongly reduced, okay? So when we look to CMB data only, I mean, in these interacting cosmologies, we are able to solve the issue. In addition, this effect is a real one because it's led by the mean value of H0. The mean value of H0 is always shifted, and not because of the larger size of the errors, okay? So it's a real effect. And there is a tendency from current CMB measurements towards an interacting dark energy cosmology, and such a preference could improve or not with future CMB observations, okay? Why in interacting dark energy cosmology the Hubble tension is solved? Because if the coupling is negative, which has to be in order to ensure the stability of the model, otherwise we will have this exponential growth of the dark energy perturbations, right? There is a degeneracy between dark matter and the coupling. Why? Because there is an energy flow from the dark matter sector to the dark energy one. Therefore, the intrinsic amount of dark matter is smaller, as you can see. As I increase the coupling, as I go to blue color here, you see that the intrinsic dark matter density is reduced. In order to have the product of omega m h squared invariant, h must be larger, okay? So I mean, since we are transferring energy from the dark matter sector to the dark energy one, we are reducing the dark matter density, and H0 should be therefore larger. So I mean, you can see this clearly here, right? And notice that the value of H0 is larger, and it's not as large as desired because we are considering W larger than -1. And there is a huge, strong anti-correlation, right, between W and H0, okay? Notice also that it helps with other tensions because the resolution of the H0 tension via a lower value of omega n implies a much larger degeneracy in the omega n sigma plane. Just because if omega n is smaller, sigma must be larger. So the allowed contours by Planck now follow a band. And there is a much larger region in which the allowed regions for the dark energy survey are Planck now overlap in the parameter space of omega n sigma. So it helps also with other tensions, okay? If now we go to the quintessence regime, we see, right, the same, the coupling, right, for different values of the coupling, omega n H0, that the value of H0 is huge, is way more larger, right? However, in this case, the value of H0 is larger, not because of the interacting sector, but due to the fact that we are in the phantom region, okay? So, the H0 tension is more efficiently solved in the phantom region because of the degeneracy between W and H0, and not only because of the presence of the dark energy coupling, and not a Coca-Cola seller, okay? So, from the CMB background data only, right, a phantom and closed universe can perfectly alleviate the Hubble tension without the necessity of going for a coupling, okay? However, if one goes to the quintessence region, one really needs a coupling to solve the issue, okay? Among other possible solutions, of course. And here I show you the huge degeneracy between H0 and W, okay? So if W is more and more negative, H0 should be more and more larger and larger, okay? So the question now is interacting dark energy the panacea for all the tensions? Well, I mean, let me tell you a bit, this is work in progress, right? So the first James Webb telescope images show that massive galaxy formation mechanism linearly, okay? So the stellar mass density, here I show you, right? In massive galaxies is much, much higher. Here I show you the 14 selected galaxies, right? Newly selected galaxies. 7 out of them have masses above 10 to the 10 solar masses. And then with these 7 galaxies, they have done this study, and you can see that the stellar mass density is much, much higher. It's a factor of between 10 and 30, at residues of 8, and more than a factor of 2 or 3 orders of magnitude at high residues, at residues of 10. You can see that, right, in the rotational points compared to the expectations, which are the lines, right, for 2 mass limits. Either for masses 10 to the larger than 10 to the 10 solar masses, or larger than 10 to the 10.5 solar masses. So these results imply that the central regions of massive galaxies began forming extremely early in processes very different from the gradual build-up of the rest of the galaxies. Okay. So has dark energy something to do with this? People have used this data to constrain the possibility of a dynamical dark energy equation of state. W0 plus WA1 minus A, okay, the CPL parameterization, right? A dynamical dark energy component. The question is, can interacting cosmologies solve the issue? Maybe yes. Why? Because, I mean, there are 2 sorts of models, right? Apart of the Bell and the M-Bell, we can have either proportional to dark matter or to dark energy. So what happens is that in models with proportional to dark matter, they may or may not solve this discrepancy. Why? Because the growth of the growth equation that you can see there, right, does not change. The only thing that changes is the background cosmology. However, if we go to models in which the coupling is proportional to the dark energy density, right, the growth equation changes. And indeed, the growth can be very different in these cosmologies with respect to the lambda CDR ones. So this is work in preparation. Here I show you these 2 data points from the James Webb-telescope collaboration work, and for that model, right? For this interacting model. And in red, I show you different type of cosmologies, and in blue as well, right? And in black, you can see the lambda CDR model. So you can see that in these cosmologies, the growth of the structure is higher, and therefore the stellar mass density is going to be much higher, and indeed it can agree with the data points observed. Okay, here this is work in preparation, but these scenarios are highly promising. So I mean, rendering again these interacting dark energies as very, very appealing cosmological scenarios. Okay, so let me just tell you the summary. Okay, so 25% of the cosmologies that I asked 10 years ago thought that the dark energy sector has to be modified. Tomorrow we will see the talk of Vivian talk about Vivian Poulard about early dark energy is another possibility, of course. But not only this, of course. I mean, there is a huge fine-tuning problem in the with the cosmological constant, and also with the most simple quintessence models that maybe can have an answer. I mean, they are unknown sectors. Why they are not going to interact among themselves? I mean, it's very logical to assume that they might show unexpected interactions, right? So there is an extra source of acceleration for the dark matter fluid in some interacting dark energy models, leading to a violation of the weak equivalence principle. It will be extremely challenging to observe interactions between dark energy and baryons, even for future surveys. The neutrino constraints from cosmology, we will hear more about this on Thursday, but should be regarded as robust because they don't depend on the fiducial cosmology. And there is a tendency from all current semi-measurements favoring an interacting dark energy cosmologies. There are a way also to solve to alleviate the Hubble constant tension. And a phantom flow universe also solves the issue. And baryon acoustic oscillation data often soften these abilities. And this is the work in preparation I just mentioned, that larger dark matter flows in interacting dark energy models may provide a compelling solution to early massive galaxy formation from the first results of the JWST-telescope. Here I tell you thank you in many languages that of course I don't speak, but okay. And thank you very much. And now you have questions. Yes.
Yeah, very nice talk. And actually, interacting models are the ones that can challenge lambda CDM because they give better fits, even considering information criteria. My question is the following. I mean, strictly speaking, we expect the interaction rate between dark matter and dark energy to be a local effect, right?
Yeah.
If we're writing the interacting Lagrangians in particle physics, it depends on the local things. I know that in all these models, we need these eights in the proportional factors. So in all the models that we consider, the interaction rate depends on 8. So this is a global feature of the universe. So strictly speaking, this is quite strange because you expect that the interaction rate between dark matter and dark energy here depends on the global feature of the whole universe. So probably some people say that this is the weak point of this, not of interactive cosmology, of these particular assemblies.
Yeah.
So probably, one can consider other assemblies that do not depend on.
There are models which instead of being proportional to H are proportional to H0, for instance. So they are more like local in this sense, right? Artificially, I have to say that it's also very, very practical because if they are proportional to H, you can handle them analytically, right? You don't need to solve them. Yeah, exactly. But I would say that it can make sense in the sense that also perturbations in H may affect these interactions, right? So in this sense, I think that to assume that they are proportional to the expansion rate of the universe makes somehow sense. Of course, as I said, they are pure phenomenological scenarios, the ones I talk about today. There are some of them which can be expressed as couple quintessence and then as f of gravity theories, which are another very appealing alternative to lambda CDM models, at least under my viewpoint, okay? I'm a modified gravity law, let's say this way. So, but proportional to H, yes, why not?
Thank you very much. Very nice talk and very comprehensive. I have this question which is a little bit connected with the one by Lars. Is it possible, in general, by this mechanism, select some characteristic length at which everything the transition between dark energy and dark matter?
Not in these models, no. But you can build on some other models in which, of course, you might have this. Yeah, more like oriented to couple cosmologies, for instance. Couple quintessence, sorry.
So you have to put up
In couple quintessence, you might have this effect that also might even include a screening effect. You know, I mean, even a screening effect to avoid, because since couple cosmologies are so close to F of R theories, you may have this also sort of mechanism or alternative description. But in these pure phenomenological ones, generally they are proportional to A or to H0.
Thank you for the talk. Well, you said that the interacting dark energy models can alleviate the H0 tension. Can you please say something about how does it work with the sigma 8 tension?
Well, in the case of the sigma 8, what happens is that since omega n is in some cases, okay, for some values of if the coupling is negative in general, the amount of intrinsic dark matter today is going to be reduced, right? Because there is an energy flow from the dark sector from the dark matter sector to the dark energy one. Then H0 should be larger. Then since omega n is smaller, in order to satisfy the observational constraints and the normalization of the power spectrum, sigma 8 must be larger, okay? So it's what happens, right? So then there is a much larger degeneracy in the omega n sigma 8 plane. And then, of course, this favors the possible overlapping between the favored region by DS, for instance, and Planck, okay? Is due to a larger degeneracy in that plane, okay? In the omega n sigma 8 plane. Also, one can think about this in another way. I mean, the growth of a structure in some of these cosmologies is going to be larger, so it's going to affect also the sigma 8 parameter, okay? So.
There is a question from
Yes. So, Malte Nascu is commenting. Thank you for a very interesting talk. Perhaps you could comment. Several recent studies have shown that JWST early massive galaxies are not in tension with non-negligible.
What? There are
several recent studies.
Yes. I mean, of course. I mean, the tension is not as significant as the Hubble constant tension. It's just something we are playing with that. Of course. I mean, this is something that I mean, there are some claims that there are not such a tension, but I'm assuming that there is. So, in this case.
Very quickly. So you have a lower matter density in OZ, right? The JWST, is that a higher matter density of an IZ? That's what's going on here?
No, I mean, the point is that we have this happening in dark matter and dark energy, right? So, I mean, in some models, in some interacting dark models, what happens is that the growth of the structure is much larger than in the Lambda theory. So, with a larger growth of the structure, you can change the stellar mass density, right, which depends on the growth of perturbations.
But you are finding a lower omega n interface.
Yeah.
And that explains why we get a higher H0 and sort of it's correlated to
You have a lower omega n, but you have also a much higher growth of perturbations.
No, what's happening at JWST? It's not anything to do with omega n. It's still 0.2 or whatever it is. Is that what I'm trying to understand what the claim is here on omega n? On matter density.
On the matter density, I mean, but this is something for the H0 stuff. I'm talking now for the James, with James Webb, the issue here we are playing is with the growth of the structure. Okay, regardless, omega n is smaller. The growth of perturbations can be much higher in these cosmologies because you have these extra terms in the perturbations, okay, which depend on the energy flow. And then playing with that, you can hide the stellar mass density, which depends on the growth of perturbations, of course, and have an enhanced stellar mass density. Of course, this is the general with omega n, right? I just saw we need to do a proper Monte Carlo to make sure that all the generacies still favor this. This is just a project which we use. Let me just go fast. Okay, yeah, if I can. Okay, I can show you later, if not. But I mean, the several curves correspond to different values of the of the matter density. You see, right? If I go to a lower matter density, right, like the solid blue curve has a much less expectation than the dash one, which assumes a higher matter density, okay? So, yeah, good point, yeah, sure. One needs to be fair.
Other questions? No?
Yeah, I will.
Maybe I would like to ask more about the role of prior and H not in this kind of analysis.
In this one?
Yes, because what we're doing in practice is actually that we look at the expansion pieces ranges, like plant topology, at redshift, and then we modify, its extrapolation at low redshift, yes? And then we have to be really super careful that absolute magnitude of type 1 supernova from inverse distance ladder is consistent with classical.
Yeah.
Is there a danger that we solve H naught seemingly, but we get mismatch between these two absolute magnitudes?
I don't think so, but you mean from the name from
No,
in general?
In general,
I don't think so, but you can really work. Yeah, we have to say that. Okay.
So,
Yeah.
we have tomorrow, okay, so thank you again.